Hello once again. If you're looking for a good song that you've probably never heard, give November Rain by Guns N' Roses a listen. Other than that, we're going to get right to this. Problem set 5.4 key, fundamental theorem of calculus. So the fundamental theorem of calculus is this thing right here, which this means find the derivative of the integral. We know that an integral means antiderivative, so if you find the derivative of an antiderivative, you're just going to get this function back. Except, let's imagine that the antiderivative is capital F. And so that means the integral from a to x of f of t dt is equal to capital F of t evaluated from a to x, which is going to be capital F of x minus capital F of a. That's something we already know. But we're actually finding the derivative of this thing. So when you find the derivative of capital F, it becomes little f of x. And then this is a constant, because a is a constant, so we plugged a number into a function, and of course you get another number. And therefore, this goes back to 0. So when you do the derivative of this, this is going to change back to little f of x. And that's why it seems like in this definition that our t that we started with kind of magically changes into an x. It's because we plugged that bound in when we found the antiderivative. But the antiderivative is not a step that we actually show or need to show. Sometimes we can't even find the antiderivative. Now we could find the antiderivative in a, but we don't need to. The derivative of the antiderivative is just the given function with the bound plugged in. Now, let's come back up here real quick. Let's assume our upper bound instead of x was like x squared. And then that would change this upper bound to x squared. And now we're evaluating f of x squared. And so our inside function has changed to x squared, which means when we do the derivative, and we get the derivative of the antiderivative, so we come back to this little f of x, it becomes f of x squared. So notice how the inside function is now x squared, which means you have to multiply by the derivative of the inside, which is 2x. But the derivative of the inside function is just the bound. Because literally, we took it and we put it inside the antiderivative. So it becomes the inside function. That doesn't come into play until the second page, but seemed like it was worth mentioning. Alright, so the derivative of this is just 1 over 1 plus x squared. Technically times x prime, because our upper bound is x, or one of our bounds is x. Doesn't matter if it's the upper bound or lower bound. But that's 1. Here our bounds are switched. If you switch the bounds, school started. If you switch the bounds, then that would switch the order of this subtraction. It would become f of a minus f of x if we did the integral from a to x, x to a. So if we were looking at this integral, from x to a of little f of t dt, trying to squeeze that in there, it would equal this. And now when you do the derivative back, the f of a goes away, and now you're left with negative little f of x. And so that's why when you switch the bounds, it becomes negative instead. And so down here, this is going to be negative cosine of t. Okay, and then 3 and 4, same question, just worded a little bit differently. So all you got to do is that's going to become x, so it's square root of 1 plus x squared. That's going to become x, so it's cosine of x. Alright, now here's something I already talked about, where our upper bound is now x squared. So the derivative is going to be, the derivative of the integral is going to be cosine with the bound plugged in. But then, since the bound is plugged in, it's your inside function, so you got to multiply by the derivative of the bound because it's your inside function. And you get times 2x. And that is why the result is different. It's because our upper bound is more than, it's a function of x, but it's more than just x. So the derivative of it, in other words, is not 1. Okay, number 6. This one, the bounds are switched, so it's going to be negative 5x cosine x. Now coming to 7, you can see on the key how you can split this up based on the hints. But you don't need to do it that way either. That was just one way in case you were kind of stuck. But really, this is still just doing upper bound plugged in minus lower bound plugged in into the antiderivative. But then we're going to take the derivative back and get the function we started with. So it's 1 over 2 plus e to the upper bound, which is x squared, times the derivative of the upper bound, and then minus the lower bound stuff plugged in. So minus 1 over 2 e to the 2x times 2. Okay, evaluate this integral. Now this was intended to be done without antiderivatives. And so if we have this from 0 to b, and let's say this is 0 to a, and the line is y equals x, then what we have is an a by a green triangle right here. So the area of that is 1/2 a squared. And then the whole triangle is going to be 1/2 b squared. And then the question is, how do you find the whole area, or sorry, not the whole area, but how do you find just from a to b? That's the question in part A. And as you can see, you could do the whole area minus the little area. So it's 1/2 b squared minus 1/2 a squared. And that's just illustrating why you're subtracting when you do the antiderivative. Because if we actually found the antiderivative, you should know at this point that it's x squared over 2. Evaluate it from a to b for this integral right here. That's supposed to be a b, I wrote 2. It's the second letter of the alphabet, does that count? So that's b, and you get x squared over 2, or sorry, b squared over 2, minus a squared over 2, which is exactly equal to this thing right here. Let's go with the lightsaber. So this is equal to that. And so it's just kind of a visual representation of why the antiderivative with the upper bound minus lower bound plugged in works, because you're getting rid of area that came before b that's not between a and b. Alright, part 2 of the fundamental theorem of calculus is what we already know. To evaluate an integral, plug in the upper bound, or find the antiderivative, plug in the upper bound, plug in the lower bound, and subtract. Alright, so what is an antiderivative of x squared? Remember, when you don't have bounds, all antiderivatives will have a plus c, so it's x cubed over 3 plus c. This one's going to be x to the negative second over negative 2 plus c. My good stylus fell out of my pocket in my car, and I didn't know it until I got in here. So this stylus I'm using is kind of sticky. It's why my 2's aren't writing very well. Negative 2 over negative 2. All right, and then we can generalize that in number 12. If you notice, hopefully when you do the antiderivative of a power function, and only a power function, only x to a number, no other function will this work for, you just add 1 to the power, because we're going backwards, like backwards power rule, and then you divide by that same number. And then of course we have our plus c. Okay. Evaluate each integral by using part 2. That just means find the antiderivative, plug in upper bound, plug in lower bound, subtract. So the antiderivative of negative cosine is negative sine of x. Evaluated from 0 to pi over 3. And yeah, you need to know like your basic unit circle stuff. It's almost always axes values that are given, but not all the time. So you do need to know like sine and cosine of other angles other than just like 0 and 90-degree angles. So you get negative radical 3 over 2 when you plug in the upper bound, minus technically negative 0, I guess. I'll write it like that, because the antiderivative is negative. So we have minus from the fundamental theorem of calculus, and then negative because we have this minus right here. Alright, and then that's just negative radical 3 over 2. This antiderivative, I'm just going to show the antiderivative. You can see the key, the handwritten key for the work. But once you know the antiderivative, it should be relatively straightforward at this point, hopefully. If it's not, you should probably come in and ask me a bunch more questions. So this is just doing power rule for antiderivatives twice. So I added 1 to 4 and got 5 divided by the same number. This is a 1, so I added 1 to it divided by the same number. And then you evaluate this. Make sure you put this in parentheses when you show this, because we're evaluating this whole function from 1 to 5. So plug in 5, plug in 1, and subtract. Okay, here we have a fractional exponent, but the power rule still works. And so the antiderivative is x to the 6/5 plus 1, which is 11/5. And then you have to divide by 11/5, which is the same as multiplying by 5/11. And then evaluate that from 0 to 5. You can use a calculator for that arithmetic, but don't use a calculator to do the actual antiderivative. If you're not comfortable with antiderivatives, especially the ones I'm going over right now, you need to revisit your bookwork for this section, because you need to be able to do these antiderivatives quickly. You should know right away that this antiderivative is x to the 4th over 4 plus x. And those become rather simple when you've done enough practice. Okay, and then plug in the upper bound, plug in the lower bound, and subtract once again. All right, now the total area, remember this is area above minus area below. So you're supposed to be able to do these without a calculator. Again, you can do the arithmetic with a calculator, but you need to understand what this graph looks like without a calculator. So if we find the 0 of this, so x cubed minus 7 equals 0, that occurs at cube root of 7. And so you should know that x cubed minus 7, you should know what that graph looks like, roughly. It's going to be just x cubed shifted down 7, so it looks something like that. And then here's the intersection point we just found, right there. So that's the cube root of 7. And so we're looking overall from 0 to 5, because that's what the problem tells us right there. And so we're going the integral from 0 to cube root of 7. And that's going to be a negative value because it's below the x-axis. So I'm going to put a negative in front of that to make it positive. And then so we're going to do the integral of that from x cubed minus 7 dx, and then add to it the area above the x-axis, which is the integral from the cube root of 7 to 5 of x cubed minus 7 dx. Okay, so find your antiderivatives. Plug in your upper bound and lower bound here and subtract. Don't forget that negative. Do the same thing here. This answer better come out positive. If it didn't, you did something wrong. This answer should come out positive. If it didn't, you did something wrong. And then combine those two answers. Okay, same kind of problem here for sine of x from 2 to 4. Again, you should know what the graph of sine looks like. Starts at the origin, goes up, comes down, like that. You should know that this is at pi. And you should know 2 is less than pi. And then this is 2 pi, which you should know 4 is less than that. And 4 you should also know is greater than pi. So the region we're looking at is like here to here roughly, or whatever. It doesn't really matter. All I need to know is what's above and what's below. So from 2 to pi, it's above. And from pi to 4, it's below. So I have to do the integral from 2 to pi of sine x dx. That's above the x-axis, so keep it positive. And then subtract the area below, because that will be a negative number. And so we have to make it positive by subtracting it. Okay, so find your antiderivative, plug in upper bound, lower bound. You need a calculator for this one because those values are not on unit circle. All right, and then finally, find the area of the shaded region of the graph to the right. So to find this shaded region, I think there's a couple of different ways you could do it. But I'm going to do, I notice right away that there's a rectangle right here. So I'm going to do the integral of sine from pi over 6 to 5 pi over 6. So from here to here, I'm going to do that integral, which is going to give me this shaded region plus the red shaded region. And then I'm going to subtract the red shaded region. So it's just the integral of sine x dx from pi over 6 to 5 pi over 6. If it'll let me write it. There we go. Oh. So that gives me the area of the red and the gray. And then the red area is pi over 3, which you can get because we know this length right here is 4 pi over 6, which is 2 pi over 3. And this height is 1/2 because you can just evaluate the sine of pi over 6 right here, or the sine of 5 pi over 6, whichever one you want. It doesn't matter. They have the same y value. And so that area is pi over 3. And so get your blue area by finding the antiderivative, plugging in the upper bound and lower bound, subtracting, and then subtract pi minus 3. So it's a good exercise for you guys to go through and find these antiderivatives yourselves, plug in the upper bound, plug in the lower bound, subtract, make sure you can get these numbers correct on your own. But you can look at the handwritten key for the actual worked, like all the way worked out solutions. All right, see ya.